Lithium metal batteries will not just improve electric vehicles. They might make the electric vehicle you are about to buy feel obsolete before you finish paying it off. That is the thing nobody at the dealership is telling you. While you are standing there comparing trim levels and debating whether the premium paint job is worth it, a handful of laboratories and pilot factories scattered from California to Japan are quietly rewriting the rules of what a battery can do. And if the timing works out, the car sitting in your driveway in 2028 could be separated from today's best electric vehicles by a gap that feels less like a model year update and more like the jump from a flip phone to a smartphone. So let us talk about what is actually happening, what the numbers really mean, and why the timeline matters more than any single headline you have read this year. The core idea behind lithium metal batteries is almost insultingly simple once you understand it. Every mainstream electric vehicle on the road today uses a graphite anode inside its battery cells. Graphite works. It is proven, it is manufacturable at enormous scale, and it is safe enough that millions of people charge their cars in enclosed garages every night without incident. But graphite has a ceiling, and the industry has been bumping against that ceiling for years. Lithium metal throws graphite out entirely and replaces it with pure metallic lithium as the anode material. Because lithium metal stores dramatically more charge per unit of mass and volume. The energy density of the resulting cell is in a completely different league. We are talking about a potential jump from the energy density of today's best cells to something that independent researchers and companies like Solid Power describe as 440 watt-hours per kilogram and 930 watt-hours per liter. For context, the best mass production cells in vehicles today sit well below half of that figure on the gravimetric side. Stanford researchers reported in 2024 that lithium metal batteries could enable somewhere between 500 and 700 miles of range in future electric vehicles. That is not a marketing slide. That is peer-reviewed science. Here is the part that should genuinely make you stop and think. The energy density advantage does not just mean more range. It means you could theoretically keep the same range as today's vehicles and cut the battery pack weight nearly in half. And in a vehicle, weight is money. Weight is efficiency. Weight is handling, tire wear, suspension cost, and the load your brakes have to manage every time you slow down. A lighter pack means a lighter car, which means less energy consumed per mile, which means the range advantage compounds on itself. Toyota has publicly targeted a 10-minute charging time and a range of 1,200 kilometers for its solid-state direction. 1,200 kilometers. Written out like that. That number does not feel like a car battery specification. It feels like a fuel tank from a different era of transportation entirely. Now, here is what they are not putting in the press releases quite as loudly. The reason lithium metal batteries are not already in your driveway is a problem called dendrite growth, and it is one of the nastier puzzles in applied electrochemistry. When you charge a lithium metal cell, the lithium does not always plate back onto the anode in a smooth, even layer. Instead, it can form tiny needle-like structures called dendrites that grow through the separator, cause internal short circuits, and in the worst cases create the kind of thermal event that no car owner ever wants to experience. Controlling dendrite growth across thousands of charge cycles, across a range of temperatures from a Minnesota winter to a Phoenix summer, and at the kind of fast charging rates that make electric vehicles genuinely convenient is the central engineering problem that has kept lithium metal batteries in the laboratory for decades. The companies that crack this problem reliably and at manufacturing scale will hold one of the most valuable patents in transportation history. The leading approach is pairing the lithium metal anode with a solid electrolyte instead of the liquid electrolyte used in conventional cells. Solid electrolytes are less flammable, and under the right conditions they can physically suppress dendrite formation by being harder for the needle-like structures to penetrate. This is why you hear the terms solid-state and lithium metal used almost interchangeably in industry coverage, even though they are technically distinct concepts. The solid electrolyte is the architecture that makes the lithium metal anode practical enough to consider putting in a car. But solid electrolytes bring their own set of problems, including interface resistance, mechanical cracking under the repeated expansion and contraction of charging cycles, and manufacturing processes that are far less mature than the liquid electrolyte production lines that have been refined over 30 years of lithium-ion production. So who is actually closest to solving this? QuantumScape moved into pilot production with what it calls its Eagle line in 2026 and is positioning its QSE-5 platform as a commercial solid-state lithium metal product aimed at high specific energy, fast charging, and strong safety characteristics. Solid Power reported its performance figures and stated in May of 2026 that work on its pilot line and electrolyte production is progressing. SESAI had 100 ampere-hour lithium metal cells passing safety tests in China in 2024, and collaborative research published through the University of Chicago in 2025 demonstrated greater than 80% capacity retention after 1,000 cycles by optimizing charge and discharge rates. CAT, the Chinese battery giant, that already supplies a significant portion of the world's electric vehicles, announced a breakthrough in lithium metal battery research in 2025 and has the manufacturing infrastructure to scale faster than almost any competitor if its chemistry matures. And then there is Toyota, which has been arguably the most aggressive in public communication about its solid-state ambitions, repeatedly targeting commercialization in the 2027 to 2028 window. Toyota has also spent decades quietly accumulating solid-state battery patents. Whether that translates into a genuinely competitive product on schedule is a question the industry is watching very closely. Here's the question worth putting in the comments right now, because it is one the engineers and investors are genuinely divided on. Do you think any of these companies can hit true mass-market production before 2030? Or is this another case of the battery industry overpromising by 4 or 5 years? Because that gap between pilot production and a car sitting on a dealer's lot in meaningful volume is where every promising battery technology in the last 2 decades has stumbled. The chemistry works in the lab. The manufacturing process is where the economics either click or collapse. What does this mean for Tesla specifically? Tesla's advantage in the current era is built on a combination of vehicle efficiency, charging network coverage, and software integration. Lithium metal batteries do not necessarily threaten all three of those simultaneously, but they do threaten the one that is hardest to maintain with incremental chemistry improvements, which is energy density. If a competitor arrives with a factory-validated solid-state lithium metal pack that delivers genuinely superior range and faster charging at comparable or lower cost, the gap between a Tesla and a well-executed rival narrows in a way that matters to buyers. That is not an immediate crisis for Tesla. It is a gradual pressure that builds through the back half of the decade as pilot lines mature into real production volumes. The honest read of where things stand in 2026 is this. The science is no longer theoretical. The performance numbers from credible sources are real. The companies working on this are not startups with slide decks. They are organizations with working pilot lines, automotive partnerships, and in some cases, delivery agreements with major manufacturers. The timeline for niche and premium vehicle applications points toward the late 2020s. The timeline for the kind of broad mass-market deployment that would make today's electric vehicle feel meaningfully outdated is more realistically a 2030 and beyond story. Buying an electric vehicle today is not a mistake. But understanding what is coming means you can make that decision with open eyes rather than discovering 2 years from now that the industry quietly crossed a threshold while you were not paying attention. For everyone who does not want to be caught flat-footed by the next shift in this industry, whether it is battery chemistry, charging infrastructure, or the competitive moves that nobody is broadcasting clearly, subscribe so you are part of the conversation before the headlines catch up.